All right. Good morning, everybody. Hope we're doing well this fine Monday. As we wait for everybody to get in, set up, I'd like to remind everybody to go ahead and type something in the chat so that I know you're here. I have record of it and all that. All right, so we'll go ahead and get started here. Any questions before we jump in? All All right. Well, so we've been talking about these things called functions, and the most common use of them has been in graphing. Whenever you make a two-dimensional plot of something, you have an input, which is the x, output, which is the y. So therefore, y is a function of x. But this is a simplified kind of case. You could have a function of multiple variables. So it's not just limited to y and x, and it's not just limited to two-dimensional graphing. So one of the last qualities we wanted to discuss about functions is this idea of an average rate of change. So what is a rate of change? Can you give me a definition or an example, something to jump off from? What is a rate? Something that you often deal with in your everyday normal lives. What is an example of a rate?
Isn't it a consistent change, whether it's increasing or decreasing?
So it's a change in something. It doesn't have to be, I'm not exactly sure what you mean by consistent or constant, but it's not just a change in something. It's a little bit more to it than that. Because let's say we're talking about the change in the amount of money that you have. So we'll call it the change in money. I have to switch over to a different marker. This one's dying on me. So the change in money, say you're a waiter or something, and you start your shift with no money in your pocket, and you end up with, or let's say you start with $10, and you end up with 50. The change is what you ended up with minus what you started with. Is that a rate? Employment is a especially this level type of employment is a great example of something where you see a rate in your everyday life. But this is not a rate. $40. It's just a number. So what else do you need to make it a rate?
Wouldn't you need points to put it on a graph?
No, it's not just about graphing, because I could plot this on a graph. $10, $50. Don't think about it. I don't want you to think about it algebraically yet. I'm trying to get an example of something in your normal life where the word rate comes up. This has to be a word that y'all have heard before. Come on, I know it's Monday, but y'all are better than this.
Repeat the question.
Give me an example of a rate of something. What is a rate? So
could it be like a formula or something?
you're thinking algebraically. How about your rate of speed, your rate of employment, your hourly rate? What do these mean?
Oh, something that's like set already.
Well, you can raise, so it's not necessarily set. But if someone has an hourly rate, what does that mean? So does anyone here have a job?
Yes.
Okay. How do you get paid at that job?
Hourly.
Okay.
Well,
You mean in terms of how much per hour?
Yes. So you said hourly. Let's imagine for a second that it's $20. Your rate is $20 per 1 hour. A rate means a change in one thing based on a change in another. What does it mean? So this is the change in money over the change in time. What have we dealt with in the past that looks like this? Change in something.
X and Y delta.
What is that called?
The slope intercept.
Slope. So if you're talking about the average rate of change of something, what you're asking about is the average slope. Okay, let's look at what that means in the context of this function. So you could have a function that looks like this. And this is kind of how actually do it. So the stock market looks like this. In general, it goes up, but along the way, there's a bunch of little spikes. So one of the things that they'll talk about is the average rate of change. So we can't find the slope of this thing because it's not all right. It's got all kinds of silliness going on. But what you can do is take 2 points, say this one, and use this one. So what you can find is the average rate of change of the function between these 2 locations. And when you talk about the average rate of change of something, it's just the slope of those 2 points. So, meaning it is the slope of a line that intersects those 2 points. The average rate of change between these 2 points is just the slope formula. So this is a also, this is something that you use if you've ever gone to a friend's house. So if you go to a friend's house that's across the, let's say you're downtown in Columbia, and we're going to look at a graph of the distance you have traveled and the amount of time that you have traveled. So you start off at home, and your friend's house is, I don't know, let's just say 10 miles away. So you get in your car, and you start going down the road. You're in a neighborhood zone, so your speed is, I don't know, like 35 miles an hour or something. So you're going, then you get to a stop sign, and you have to wait. So you're not moving any distance at all. I'll do points. So your line is flat. Then it's your turn to go, so you start going again. Then you hit the highway, let's say, so you can go really fast. But then to get off the highway, you're not moving because you're stuck at a light. And this is a really long light. And then finally, you can turn into your friend's house and you made it. So you might say, if it took you, I don't know, 10 minutes to get there, then your average speed would be 60 miles an hour. But you weren't going 60 the entire time. Sometimes you were going slow, sometimes you were going not at all, and you were going fast, and then you were stopped. So when you're planning out your journey, you don't think of every individual stop, every individual, all right, it's gonna take me 45 seconds at this stop sign, and then I can go 35 miles an hour. We don't think like that. What we do is we can say, okay, it might take me, eventually we shorten it down a whole lot. We might say, I can probably do about 60 on average the whole way. and then divide that by the time it takes, or the distance you're traveling. That tells you how long it will take to get there. But this average rate is just the slope between the point you started and the point you ended up. This is the idea behind the average rate of change. Is it treats something that's not a straight line as if it was, because it doesn't matter in this context what all of the individual stops are. All that matters is where you start and where you ended up. So this is the last little bit of qualities of functions we wanted to talk about. So now we're moving on to different types of functions. So we have so far talked about two different kinds of functions. We have linear functions. Oh, I'm not using the black. So equation for a linear function, y equals mx plus b. And then we also had squaring functions. So we call those quadratic. And the way that we wrote them was in this form: ax squared plus bx plus b. Okay. So these are the two that we're going to kind of start off with. And talk about their simplest possible forms. Okay. So the simplest version of a linear function, actually we'll say it like this. We're going to talk about something called parent functions. The idea here is that a parent function is like a parent to children. You can have one parent, or really two parents, I guess. Sorry about that. You can have two parents, but those two parents can create a bunch of different looking little children functions. But there are some rules. So you can't create a function that is not the same species as your parent. So two human parents can't make chicken eggs. That doesn't make any sense. But they can make different looking human offspring. So I'll show you what I mean. The simplest version of a linear function is just y equals x. This is the parent of that one. Everything else that you do to this, you can add stuff or multiply stuff in, but it's still a linear function. You're not adding, you're not increasing the number of x's. So there's still only just x to the power of 1 here. You don't have any x squareds or anything. But this is the parent function of all linear functions, because you can make any linear function just by messing with this one. For quadratics, you have a parent function of y equals x squared. So this is where I guess I find this a very helpful place to start if you are trying to graph or mess with functions. And we will talk about how we are going to take these parents and make other functions a little bit later. But these are the most basic versions of these functions. So, sorry, my internet is being slow today. So we have a bunch of these kind of basic versions of functions. The polynomial ones are very easy because they just follow this progression. You can have a parent function of y equals x cubed, y equals x to the fourth, to the fifth, sixth, seventh. So each one of these things represents a different family of functions. Linear, quadratic, cubic. These are the main three of these type that we're going to use. But there's a lot of functions that we can't create just from these basic ones. There's also the root function. And the reciprocal function. So these are the main parent functions, I guess, that we're going to be using this semester, or at the end of this semester. So, so the main idea is that you can create any kind of linear function from this parent, or any kind of quadratic from that parent. But you can't create a quadratic out of messing with a linear function, and vice versa. So they're all kind of different species, but we call them different families. But they have the same idea. And these are the main ones that we're going to use. But there is one way that we can kind of join functions together. And one of these includes a new kind of function that is pretty similar, or pretty simple, but does need to be mentioned. And that is a step function. All right, has little brackets on the outside of it like this. And those brackets mean kind of sounds funny to write it. Greatest so it's the greatest integer less than or equal to x. What does this look like? Well, so 1, 2, 3, -1, -2, -3. So the way we draw this out is, let's just graph it. So if I pick the number x equals 0.5, that's a little bit too small, I'm noticing. So I'm going to change the tallies up a little bit. So if I pick 0.5, so it says the greatest integer that is less than or equal to x. So x is 0.5. We have to basically round down to the greatest or to the lowest integer. So it will be right here out to, no, here. Let's say we go 1.5. At 1.5, the greatest integer that is less than that is 1. So, and it goes all the way down to 1. If we come over here, and we did -0.5, greatest integer for that is at -1. And -2 looks like this. So this is why it's called the step function, because it just looks like steps. Let's see if I can find a prettier version of it. So So this is the step function. This one is adjusted, but it looks like this. So you have just little stair steps. This is graphically what it looks like when you round something. Because even if your x is 0.5, you round that up to 1. And so it's equal to 1 everywhere from 0.5 right up to 1.5. Then it rounds up to 2. And then 3, and so on. So the step function is also kind of a rounding function. All right, so we'll cut it out there. But these are the, like I said, the parent functions. These are functions that we're going to take, and we're going to learn how to manipulate and create every other possible function just from these simple versions of these functions. So, yep, that's all we've got for today. And you guys make sure to have a great rest of your evening. All right. See y'all on Wednesday.